In this video, I'll be covering the first half of the Unit 3 Section 1 notes on types of chemical bonds. Specifically, we'll be covering the first two objectives, which are to define our two main types of bonds, as well as learn the octet rule. In our next video, we'll talk a little bit about identifying the different types of bonds, how we can go about doing that. So first, let's talk about our two main types of bonds. Really, bonding in general is a way of talking about how atoms are going to interact. Remember that in chemistry, we're focused on how matter or stuff really interacts with one another. So when atoms interact, oftentimes they either form or break bonds with one another, how basically those atoms stick together. Now, when we talk about atoms bonding, really we want to focus on answering the question, what part of the atom bonds? Now, let's consider the situation where these two atoms on the screen are going to form some type of bond. If we imagine them sort of crashing together, we'll notice that the first part of those atoms that comes into contact are those outer electrons, which we call our valence electrons. These are the electrons which cause the bond. That's what forms basically the glue that sticks these atoms together. So valence electrons, they're the electrons in the outermost ring of the Bohr model or the shell of, say, the quantum mechanical model. And it's not wrong to think of these two atoms as literally crashing together and those valence electrons sticking them together. Although, obviously, it is much more complex than this and more about how to minimize the energy of those electrons. So the two types of bonds, as you may have noticed on an earlier slide, are ionic bonds and covalent bonds. Both of these bonds perform basically the same function, which is to help atoms stick together. So ionic bonding. This is a situation when one atom will give up its electron and another atom takes that electron. You can see that situation on the left-hand side of the screen. And when an atom loses a negative, it becomes positively charged. So when an atom loses an electron, it becomes positive. And when an atom gains that electron, it becomes negatively charged. My general piece of advice here is follow the electron. Wherever the electron ends up becomes negative, and wherever the electron leaves becomes positive. A specific situation we can see here is if an atom of sodium on the left gives up an electron to, say, an atom of chlorine, the sodium becomes positive, specifically positive 1, because it lost one electron, and the chlorine becomes charged as negative 1 because it gained one electron. Afterwards, these two atoms, because they have opposite charges, they would be attracted to one another, kind of like magnets. So ionic bonding, that's the transfer of electrons, one atom giving and one atom receiving. Covalent bonds, on the other hand, are when two atoms share those valence electrons. We can see in the situation on the right, this oxygen over here has 6 valence electrons, 2 paired and 2 single. This carbon has 4 single electrons in the valence shell, and this oxygen is the same as its partner on the left, 2 pairs and 2 singles. What happens is all of the single atoms basically find a partner and they are shared. And we can see those partnerships sort of gluing the carbon and oxygen atoms together. These are our covalent bonds. The electrons are part of each atom. And this brings us to the octet rule. So what is the octet rule? Well, put simply, the octet rule states that an atom will almost always prefer to have 8 valence electrons. That makes it stable. And a couple of clues we can look for in the name to remember it. Remember that octopus has 8 legs, octagon has 8 sides. Octet rule means your atom should have 8 electrons in its valence shell. And if we look at, say, any noble gas outside of helium, we'll notice that those atoms have 8 valence electrons in their outermost shell, and that's why they're so stable and non-reactive. Now, if we were to take a look at the periodic table, just the S and P blocks up here, highlighted in tan, and we look at their Lewis dot structures, we can see there's one more electron being added each time we go to the right. We'll notice that we can kind of predict what's going on in the valence shell. We can kind of predict what type of bond might be formed. If we take a look at, say, lithium, for instance, with one electron in its valence shell, if we look at the Bohr model here, we can see that really this lithium is not stable. It wants 8 electrons in its outer shell, but it only has 1. So lithium really has to either gain 7 more, or it is one of the few atoms that can actually break the octet rule. Really, lithium wants a full outer shell, whether it be a full second shell or a full first shell. So lithium's either going to gain 7 to fill shell 2, or probably lose that first electron in the second shell to go down to its innermost shell. We can see a couple of examples here on the second slide. Sodium with 1 valence electron, calcium with 2, oxygen with 6, and fluorine with 7 in its valence shell. So sodium having only 1 valence electron, it is most likely going to lose that electron and go down to this full octet in shell 2. Calcium with 2 valence electrons is most likely going to lose them and go down to the full third shell in this case with 8 electrons. Oxygen, on the other hand, has 6 valence electrons. It's most likely going to gain 2 more to fill this outer shell because it doesn't take much of a change to do so. And fluorine, with 7 valence electrons, it's most likely going to gain another one to get that full outer octet. And really, what's going to happen here is these atoms somehow have to gain or lose electrons so that they have that full outer shell. So when it comes to ionic and covalent bonds and that octet rule, notice that ionic compounds, each atom has an individual full outer shell. In this case of sodium and chlorine, each atom has its own outer shell, sodium right here and chlorine right here. However, in covalent bonds, those shared electrons count towards both atoms total. If I were to say count the electrons in oxygen and carbon, I can see that this oxygen has 1, 2, 3, 4, and then counting all the valence electrons, 5, 6, 7, 8 valence electrons. All of these shared electrons are counted towards oxygen's total. And the same is true of carbon. In fact, carbon only has shared electrons in its outermost shell, and it fills with a total of 8. We will cover identifying types of bonds in the next part of this video.